All right, welcome everyone. Can everyone hear us okay? Let me double check on YouTube.
I don't see us in the YouTube yet.
All right, you guys are monitoring this, so I will just monitor StreamYard here. And should I be monitoring anything else while talking, or?
No, don't worry about it. Like we can be monitoring stuff on your behalf.
Perfect.
Mark, I think we have to make an announcement. We did not do.
The announcement is made on Twitter, and then let me make like yet another one. Sorry, an announcement is made here. We'll do another one. Okay. Well, okay. Well, welcome everyone to another like episode of GPU Mode. I know there's like an irregular, like earlier time than most people are used to. Yeah, but we're at I'm actually at ICML this week, so apologies, folks. This is my hotel room. But today we have like a fairly nice lecture. So we have Markus Hrywniak from NVIDIA, who's going to be giving us like a broad introduction to multi-GPU programming. There's a lot more lectures we're planning on the topic, and so the intent of this lecture is really to be like an authoritative like first lecture that you can go to, and then you can sort of like branch out like depending on what subtopic you're interested in. So yeah, without further ado, Markus, please take it from here.
Yeah, thanks, Mark. Thanks very much for having me. Hi, everyone. I'm Markus. I work on optimizing porting applications to the GPU, and the plan today is to give you an overview of multi-GPU programming, what that means, and how to get started. So first of all, why use multiple GPUs? So I guess if you're here, you already want to use multiple ones, but just to clarify, the two main reasons you might want to do so is either you have a problem you need to solve, but you need to compute it faster. So the classical example is you have a weather forecast, and that's fairly useless if it arrives, after the time you forecast for. So you want to make sure it arrives in time. And this kind of scaling out to multiple GPUs is called strong scaling. You use more resources to solve the same problem faster. Or you have another, let's say, a problem that increases in size, and you want to solve that bigger problem, but you want to have it take the same time, or you simply just need more memory, more other resources to be able to compute this. And this is what we like to call weak scaling. So, and also another more pragmatic reason is today's systems already are massive and they're getting bigger. And so they have multiple GPUs. And so just to efficiently use these parallel systems, you need to be able to have your code be parallel. So that's also a very important reason. For today, this introduction is meant to show you how to go from a single GPU example to using multiple GPUs. I will use three fairly common libraries or programming models, MPI, Nickel, and NVSHMEM. I'll try to make clear when to use which of these and how to profile and measure that you're getting the advantage you're expecting. And I also want to stress that how to, understand the critical path your application goes through, where latencies in the programming models impact your performance, and hopefully I'll leave you with a better understanding of how to look at going to multi-GPU. I also need to point out that most of the material I'm showing today is based on my colleague Jerry Krauss' talk series. He's been doing this for quite a while at NVIDIA's GTC conference. I've linked the two last instances of this tutorial where a lot of this content here is from. So if you, in the meantime, want to go deeper into any of these topics, I would encourage you to check out these links. All right, so that is the motivation. Let's get right into it. So our example today, we need an example application to understand these programming models, and we're going to use a Jacobi solver. We're solving the 2D Laplace equation, which is on here. So essentially, you have an unknown function u, and you have a prescription for the second derivatives in x and y direction on a certain domain, and with some boundary conditions of the border of the domain. So don't worry, this is all the math I will need today, and we are going to be just in program code for the rest of it, but just to motivate where we're coming from. So we have this example, and the 2D domain needs boundary conditions to solve this equation, and we have Dirichlet boundary conditions. That means constant values on the boundaries on the left and right. And then we have periodic boundary conditions on the top and bottom. And what that means is essentially our domain can be viewed like the surface of a cylinder that's wrapping around. So we are in 2D, not in 3D. So we have these boundary conditions left and right, and top to bottom just wrap around the cylinder, if that helps you visualize what we're doing. There are multiple implementations you can get and run readily from GitHub. So the multi-GPU programming models repository has a lot of these examples with all the programming models we're going to see today and many more. So if you want to experiment yourself and see how the actual full code looks like, please go there. But for now, we'll focus on the core parts of the solver. So doing some more mathematical transformations. This is essentially the code you need to implement the Jacobi solver. So it's fairly simple for this equation. And the general flow is that if you want to do this on a single GPU, you have a loop that's running until convergence, and convergence is measured with the L2 norm if you're curious. So we basically measure the distance between the last guess of our solution and the next guess. And to get from last to next, we have this double loop that goes over the full domain that we are trying to solve the equation on. And that full domain is here on the right. Note our coordinate axis, x goes to the right, y goes from top to bottom. So this is basically index 0, 0, and this blue dot is 1, 1. More on why we start here later. But we start at index 1, 1 in y and x direction. So we go through all the rows, and then we go for each row through all the dark green dots. So this is the second loop here. And to update, we essentially need to average all the neighboring dots. So this is really what this equation means. I will just explain the indexing a bit. But if you look at the visualization, you see this blue dot basically needs the right, left, top, and bottom neighbors. We add those up, divide them by 4, and then we have the new value for the next iteration, essentially. So we have a one-dimensional array, and this is in the C programming language. And we want to use two-dimensional indexing by essentially having a y and an x index, and the number of elements in each row is nx. And so this is how you get to these indices here. So you have the current row, and then you go 1 to the right, ix plus 1, 1 to the left, ix minus 1, one row earlier, so the row above, iy minus 1, and the row below, iy plus 1. So that's all we need to do. Then we need to apply these periodic boundary conditions, which means the left and right borders here are fixed. Try to visualize this by this gray dots. And the top and bottom boundaries are essentially mirrors of the actually computed values here. So this mirrors the last row, and this here mirrors the first row. So in that sense, this is all periodic and wrapping around on the surface of the cylinder. So after we've done the update, we swap our buffers A, nu, and A, do the next iteration, check for convergence, and this is essentially all you need to do to solve this equation iteratively, numerically. So far, so good, but that's single GPU. And if we want to go to multiple GPUs, what we need to do is we need to somehow do a domain decomposition. That means we need to take our simulation domain, split it up into separate chunks, and have each GPU compute only one of these chunks. One choice is to divide it horizontally in stripes. We can divide it vertically in stripes. You can also do kind of a mix between, divide it into tiles by dividing both horizontally and vertically. And they have each pros and cons, such as the amount of neighbors you need to communicate to, or the amount of data you need to exchange in total. For us today, we're going to choose horizontal stripes because that's very simple in our model, because we have contiguous data in each row. So we don't need to do any special packing for exchanging the data with neighbors. And we also don't have a high amount of data to exchange. So let's see if we split our simulation domain in that direction, what we need to exchange in our code. Actually, not a lot. So the main thing we need to do is to recognize that our local contribution to this whole solution that we want to do now starts at a different index and ends at a different index than the global amount of rows. So the global amount is really much larger than the local simulation domain. But we also run into some complication, because if you look at this blue dot here, it still needs the value above, but the value above is now no longer computed locally. The value above is actually computed here. And so that means we kind of need to exchange data between neighbors along these boundaries. And this is what we call a halo exchange. A halo exchange because the last row kind of shimmers over to the next rank and so on. And this row kind of needs to be mirrored over here, symbolized by these arrows. And so what we now need to do is we need to change our periodic boundary condition implementation to just really do a ring exchange and exchanging all these boundary rows between neighbors to be able to continue with our solution of the equation. Let's think a bit how we can do that. So we need to exchange messages with our neighbors, essentially. And one of the standard libraries that's available for doing this is called just message passing interface, or MPI for short. You may have heard of this. MPI is a library that's been available and very mature for a long time. It's actually not just a library, it's a standard. It's a standard to exchange data between different processes. And the API consists of many, many separate functions. The most commonly used ones are sending and receiving data, but there's also collectives such as reduce, all reduce, and broadcast, and so on. And the standard specification and more information is available on their website. What's important for us now is that there are many implementations, both open source and commercial, available for essentially any language you can think of. So today we're going to stay more in C and C++, but you can also use it in Fortran and Python and really any language. The other thing that MPI provides besides the API is also a facility to launch multiple processes in a way that they can talk to each other and also exchange these messages, but we're not going to go into much detail on this today, just that this is an important point to have. All right, so now let's see how we can actually get to exchanging data between our processes here. We first need to kind of understand how to make our process MPI, an MPI process. And that is, you need a couple of extra library calls. You include the header file. You need to initialize the library by calling MPI init. That kind of sets up all the scaffolding so the processes can call the other APIs. And once that is done, these are the first two calls you will probably find in any MPI program. MPI defines something called the communicator, abbreviated with COM, and the concepts of rank and size. By default, when you launch an MPI program across multiple processes, each process is part of the MPI COM world communicator. And inside that, it has an index. That's the rank. So each process has its own unique index there. And the total number of participating processes is the size of the communicator. And so what we do here, we retrieve these values, and after that, we can use them in our control flow to determine which part of the domain we actually need to compute locally on our process on our GPU. When we're done, we shut down MPI again, and that's basically the skeleton of an MPI program. If you now go to our Jacobi solver code, I've expanded a bit the code we are displaying here, and I will go through this now line by line so you can follow along. We still have this outer loop that was hinted at earlier, where we check for some conversions and we count the iterations we've been doing. So this memset async is more, it's needed to reset the norm that we accumulate while we solve our part of this whole simulation domain. So we set this to 0 asynchronously on the computed stream, CUDA stream. Then we actually launch our kernel that is responsible to generate a new out of the previous value A. And we have the other parameters, such as where the norm should be written to, the start of our domain and the end, number of elements in a row. And this is also enqueued on the CUDA stream compute stream. Afterwards, we have the CUDA event record call to put an event on the stream. And that event is meant to, for us, be able to check when the previous kernel is done. So this will be important in just a couple lines further down. After we enqueue this, so remember, this is all asynchronous, so we're not waiting for anything yet. We enqueue another mem copy, and this is done to retrieve the L2 norm that's been accumulated locally here to a host variable. So this is why you have a mem copy device to host, also on the compute stream. And after we've enqueued all these 4 operations, we finally need to do some synchronization eventually, because we need to make sure that our kernel has done computing the interior part of the domain so that we can start exchanging data with our neighbors. And so this is the first sort of puzzle piece we need to be able to figure out where to send data to. So remember, the rank is kind of the index of our process in all processes that are running. And what we do here is we check if we are not the first process, so if our rank is bigger than 0, and then the top neighbor, because our y-axis goes from top to bottom, the top neighbor then is 1 rank less, and this is where we need to send our message. Otherwise, if we are actually rank 0, so we don't really have a top neighbor, we instead send one message to the last process, last GPU in the chain, because of these periodic boundary conditions, so we wrap around. And similarly, what we do for the bottom neighbor, usually it's just incrementing our rank by 1, except if we are already the last rank, then our bottom neighbor is again the first process in the chain. So when we have figured out these neighbors, we can start doing our Halo exchange that I will show on the next slide because it's a couple more lines of source code. Let's just say we exchange messages and we now finally are ready to really synchronize the compute stream because we need to wait for all outstanding operations to complete. At this point, we then take our local L2 norm contribution, or more accurately, the squares. If you know how the L2 norm is calculated, you accumulate the squares of the differences, and then you need to take a square root. So squares can be just summed up. This is why we do this all reduce, which kind of takes from all processes that are participating the accumulated local norm, sums them up, and then every rank has L2 norm accumulated overall, and then we can take the square root and use this for the next convergence check just after swapping buffers and incrementing the iterator here. All right, so that is basically the full iteration. Now let's look at how this Halo exchange actually is implemented with MPI. Again, we have here our participating domains. So we have the left and right boundaries, we have these Halo rows, and we have the interior. And the easiest way to do such a neighbor exchange between the top and bottom neighbors in MPI is with a send receive call. So this is a combined send, essentially the first row here, and receive call, the second. And this is really just where to do the send, and the status here we can ignore. So what we need to do is, and let me just jump one step ahead because then I have some graphical utilities to show you how this helps. So our local process here needs to send the first row it has computed into the Halo row of the top neighbor. So this means here's the top neighbor. We have float data types. We have NX elements because this is how many we have in one row. And the indexing means we basically offset from the start of our array because the first elements in here are our own Halo elements. We offset by IY start, which here is 1 because our Halo is really just one row. So we go here, send these elements to our top neighbor, and at the same time, we post a receive operation expecting our bottom neighbor to send us their top elements into this row, which is essentially this second row here. And now we have basically one half of the Halo exchange. We have exchanged Halo with top and receive from bottom, but we also need to do the complementary operation. We need to send our last row, our bottom row, which is this one here. So these elements need to send to our bottom neighbor. And conversely, we need to post the matching receive so that our top neighbor can send us the Halo rows it itself has computed. So this is essentially two send and two receive calls. And the nice thing about this API here is it combines both of these together, so we can be sure we don't get into any kind of deadlocks because one rank is waiting for send that the other cannot yet post because it itself is waiting. So this is very nice that we can combine this together. And in the end, all of this is from the view of one local process, as you can see here. But since all the processes themselves execute the same send receives just with different values for bottom and top neighbors, and of course, different local arrays, it all fits nicely together to implement this whole wraparound Halo exchange between everybody. So this is essentially just code that would have also worked on the CPU. And yes, indeed, there is not a lot of things you need to make it happen to also work with GPU buffers. And why that is, we'll now look at, because one very important thing here is that all these buffers are pointers into one unified virtual address space. What does that mean? It means that memory that is physically belonging to the CPU or physically belonging to the GPU, because those are different, usually different. You have a plugged in GPU maybe that has its own memory. You have the CPU with its RAM, but you can address both of these locations with the same kind of pointer. And because 64 bits is really a lot of bits to address a lot of memory, we can just say that some basically fraction of these addresses just can be detected to belong to the GPU memory. And this is exactly what the MPI library or the underlying libraries are doing when you pass it such a buffer. It looks at the pointer value, it can call an API like CUDA pointer, get attributes, and then do the right thing and see if this is a GPU buffer or if it's a CPU buffer. And then under the hood, it might launch a mem copy or might do any other kind of operation without you really having to do anything actively. Support has been around for a long, long time. So Compute Capability 2.0 is really so many years ago that on today's systems, you can expect this to be available. let's look at what else this enables, because there's a range of technologies called NVIDIA GPU Direct, and one of these is a GPU Direct peer-to-peer, and that means if you happen to be on a system that has multiple GPUs, like this one with its memory, and another one with its memory, and a CPU with its memory, and the GPUs are connected via NVLink, that the data transfers can actually go directly from the memory from one GPU over NVLink to the other GPU without any involvement of the CPU in this case. Or another similar technology, which is called GPU Direct RDMA for remote direct memory access, that allows you to take the memory from GPU here and send it out over the network over InfiniBand, which is here the IB short for. And that means the network card can just read the memory of the GPU, send it out, or write it on the other node, which is receiving, without really the GPU having to actively do anything. And this is all what the MPI library and other libraries will do behind the scenes to make it very efficient. One word on how you should launch your MPI processes, because this is important. We usually expect to have one process per GPU. So if you have 4 GPUs on your node, you launch 4 processes on that node, and that times as many nodes as you have in your whole system. There are different launches to do so. MPI usually ships its own MPI run, but there are also cluster software such as Slurm, which have srun, or as we'll see later, NVSHMEM also has its own launcher. But the important part is that you remember to launch one process per GPU, and then the launcher takes care to assign a rank to each of the processes, each of the GPUs, or as we'll see later, NVSHMEM calls these processing elements or PEs. So just that is one important consideration I wanted to highlight. But now let's just look at practically when you do such a transfer, what the send receive will actually trigger under the hood. Because we want to keep it simple, we don't do the send receive as one call. We have just 2 ranks on 2 different nodes. Rank 1 posts the MPI send from GPU buffer, and rank 0 posts the send, and rank 1 posts the receive. And then we'll see how the data travels over all the different components from the memory of the GPU on node 0 to the memory of the GPU on node 1. So the best case is you have a CUDA-aware MPI, such as what we've been expecting here, and it also has support for GPU Direct RDMA, so your network card can directly read GPU memory. So that means you post a send on the send buffer, send it to rank 1, and you post the receive into a receive buffer on rank 0, from rank 0 on the other side here. And then what happens is simply the data flows directly via RDMA through the network interface onto the GPU on the other node. Now, that looks like on the timeline. So here I've profiled this with Nsight Systems, which will show you, amongst other things like GPU kernels running. It will show you, for example, that the GPU here has a PCI Express transmit throughput. So it is sending data out of the GPU, but there is no actual activity in this row. So no GPU kernels, no mem copies running. This is because it's really just sending data out over PCI Express to the network card, which is then sending it out over the network, and then the data will arrive on the other node.
Markus.
Yep, sure.
Let's take 1 minute for a couple of questions in the chat. So
Sure.
I think you answered one of the questions that came in. Can MPI send and receive data directly from the GPU global memory by any chance? And subsequently, can Nicole do that, assuming we have some interconnect between the GPU?
Yeah. Essentially, this is what GPU Direct does basically. So if you the network card reading memory from the GPU buffer is RDMA, remote direct memory access, what we're seeing here. So the over PCI Express, the data flows out of the GPU main memory, global memory, through PCI Express into the network, and the same in reverse on the other node. And yeah, peer-to-peer essentially just is if the rank 1 was not on another node, but on the same node, then it would flow through NVLink.
Yeah. Then I do have one more question to you. So
Sure.
You mentioned there is a requirement in Slurm and other methods on how we launch a process per GPU and mapping that, yes, you need to have one process per GPU, kind of like a thing.
Mm-hmm.
Why? What is the intuition for creating such a solution?
Right.
Why could not I create multiple GPUs per process?
Sure. So you can, and it's not a restriction in the sense that Slurm or MPI run really prevents you from doing it. It's just that the most efficient way that all these technologies work of directly mapping buffers between the GPUs and so on, that this works best when you have one rank that belongs to one GPU. So it will still run, but the best results for CUDA-aware MPI kind of needs one GPU per process, and that is simply just the most performant way to do it.
Okay, there are a couple of follow-ups on the same question. One is that from Rohit, who is asking, there are 8 processors on DGX machine with 8 GPUs, never understood why this is the case. And then Surya communicating, I think tying one GPU to one PE makes that symmetric address guarantee, and it makes it very trivial for it. And if you draw 2 GPUs from the same process, you would have to have 2 separate heaps of memory in one single address space, and then you have to manually ensure each GPU sees the right base pointer, and that quickly gets ugly.
You would also, yeah, there's multiple reasons. You would also, if you have your own calls, you would need to set devices between and so on. You would need to keep track where you are currently. Yeah, so it's and there's not really anything you would gain, because if you have a kernel that can fully fill up your GPU, you do it on one process. If you are launching 2 at the same time on the same GPU, first you have 2 contexts, so the 2 processes would be computing for the same GPU resources, and there's other technologies for working around this, but essentially it's just the simplest and most performant way here.
Yeah. Is one GPU per process a hard requirement for CUDA-aware MPI?
As far as I'm aware, it is, due to the way it's implemented. But I will need to check on the details myself.
So in the case of the torch distributed, I believe it also goes with 1 process per rank. I believe this basically comes from that same restriction of the CUDA-aware MPI case. But is there any other reason for it?
I'm not aware of the really low-level reasons for this. Besides that, just if you have 1 process per GPU, you only have 1 context, and so you don't need to kind of time slice or use another mechanism like MPS to mitigate kind of that you have different contexts which need to compete for the same GPU resources. So I believe it's coming from somewhere of that direction.
Okay, I think we can continue.
Sure.
Mark, go ahead.
Yeah, like my sense is it's also kind of like application dependent, like for I don't know, for things like data parallelism or model parallelism, it's just like not really crucial, I think, to lift this restriction. I think it becomes like more interesting in like things like post training, where you have like processes doing very different things. Like basically you might have someone, you know, doing serving a VLM, and then someone else synchronizing weights in a replay buffer. And I think then at that point, like the cracks in the system start showing like a bit better. And for what it's worth, like I think back in the day in PyTorch, like no one uses it, but we do have a data parallel functionality which does single process, single node GPU programming, and as far as I know, no one uses it. But yeah, like I think it exists. It's just like the other model won out.
I mean, generally you can have 1 process and multi-thread to access multiple GPUs, but it's especially in the case of MPI, which thinks about processes, usually you have multiple processes communicating. It's just mentally also much simpler to, you know, disambiguate who is doing what if you just have 1 process, 1 GPU, as many GPUs per node, and yeah.
Okay. Is 1 process per GPU a hard requirement for Nickel and NVSHMEM too?
So Nickel, you can also use multi-threaded with having different GPUs in the same process and calling set device in between, as far as I'm aware. For NVSHMEM, I'm not entirely sure. I think oversubscribing GPUs with processes on the other hand, so that you have 2 processes per GPUs, I think not supported in that case. Okay. Except, so especially if you use them at the same time. But for the details, I would also check the documentation of the libraries here.
Okay, we can move on.
Okay, sure. Good. So just to recap here, the easiest way we had basically, so the most performant was we have GPU direct RDMA and move data directly from GPU 0 to from the GPU on rank 0 to rank 1. Now we look at what happens when you can't directly move the data. So at GPU where you have CUDA-aware MPI, but you don't have support for GPU direct, potentially because your network card is not attached in a way that supports this, for example. And then what you need to do is you need to first post the same code. So code does not need to change. This is portable. But under the covers, there is a lot of extra copies, because first the data needs to flow to the host through a pin CUDA buffer. Then there is a copy into the fabric buffer for the network card to do the pipeline copy over the network, and then the same in reverse on the other node. So that means you just have a bit more steps in between. And you can actually also see this in the profile, because in addition to the PCI Express traffic going out of your GPU, you now have the sequence of mem copies from the device to the host, which happen as part of the MPI operation. So this is essentially then the difference when you can't use a GPU direct RDMA here. And now the third case we're looking at is if you happen to have an MPI that doesn't have any awareness of CUDA buffers, so it cannot do anything if you pass it a buffer on the device and would just crash because it doesn't know how to handle this data. So in this case, if you do it manually, you would need to have a manual CUDA mem copy into the host side send buffer, which is the same size as the GPU buffer. And then you can call MPI send on the host buffer, have this go through the network card again into the same buffer on the other rank. And then when the MPI receive has finished, you can now upload this to the GPU buffer here. So you see there's a lot of extra synchronization that's needed because each operation needs to wait for the preceding one to be completely finished in this case. And there's no potential here to pipeline this in a more efficient way. And what you will see then in the profiler is you will see your own mem copy that you called in the code. And then afterwards, you will see just the MPI operations proceeding. And if we now look at how this manifests itself in performance, so we have the bandwidth that's achieved on the y-axis here, and the message size on the x-axis in byte. And we have the three different variants. The CUDA-aware MPI with GPU direct RDMA is at the top. And in this case, on this machine, Joules Booster, which is a supercomputing cluster that has an HDR 200 network, so 200 gigabit is around about 25 gigabytes per second, and we are very close to that kind of peak bandwidth. If you have to do this extra pipeline copy, or the MPI has to do it, you are closer to this here, so you reach lower peak bandwidth. And if you have to do the manual staging, you are also, yet again, at about 10 gigabytes per second. You'll also see that the latency is much lower if you have RDMA available, 4 microseconds to about 24, 25 microseconds. And that's because you have just less points where you need to wait and synchronize, and so latency can be lower. For GPU direct peer-to-peer, the difference is even bigger. And that is mostly because peer-to-peer allows you to use NVLink. And NVLink is a lot faster than the PCI Express that you would be using if you need to stage through the host. So this is why you have such a big gap in here. Also, again, between the three different variations. Okay, so this is essentially what GPU Direct enables you to do. And CUDA-aware MPI is also, as an example, used by many applications in production. One such example is a weather and climate code called Icon. And in this example, we just have two variants of Icon. One of these uses, here on the left-hand side, uses MPI through the host buffers. So you have mem copies here, and then you have MPI operations. And the other variant simply uses CUDA-aware MPI, which allows the MPI implementation to take care of the copies and use the most efficient way to transport the data between the GPUs. And for Icon in this sense, it means that if you look at the scaling behavior, and the important thing that's being measured here is the time to simulate, so per one simulated day, so less better. And if you scale out through multiple nodes, in this case on EOS, which is the DGX H100 cluster, you can see between 1.4x and 1.6x improvement. And that is just because of all the gains that manifest through the CUDA awareness of the MPI and the direct copies between the GPUs, essentially. So, but this is not all we can do. And a real production application, such as Icon, would also employ other tricks instead of just, relying on CUDA-aware MPI. Because if you look at what we did so far in going from our Jacobi solver from one GPU to many GPUs. So if you essentially consider that we want to just process the whole domain, we effectively introduce overhead. We don't actually want to do communication. We have to, because our domain is now split into multiple pieces. And so one technique that gains back some efficiency here is overlapping the communication into computation. And that works in this way because we have these different points that we need to compute the update for, but remember that they only use their 4 nearest neighbors. So that means we can independently compute the process boundary domain, so just the top and bottom rows. And only then do we start with the inner domain. And when we have done the boundary domain, the inner domain is probably still computing, but we can already do the communication operation and thereby overlapping both, removing it from the critical path, and so gaining more parallel efficiency. Let's just look at what our profile is before we implement this. So we have these MPI send receive, the send receive. We have the all reduce for calculating the norm for conversion checks. And then we have our Jacobi kernel in here. And essentially, we want to move these two guys just to execute here at the same time as the kernel. So they are not basically in the critical path and preventing us from scaling further out. The change we need to implement is this. So instead of just launching the Jacobi kernel as we did before one time, we launch it 3 times, but we launch it on a different part of the domain as I suggested before. So we don't compute here the full, but just one row. So IY start to IY start plus 1. This is essentially one row of the inner domain. Then we do the same for the bottom row. So IY end minus 1 to IY end. And then this is the inner part that is needed to fully finish all the computations. We do these on 3 separate streams, on push top stream, push bottom stream, and compute stream. And that means when we need to synchronize to do our send receive, so do our communication, we don't need to synchronize on the full computation, but we just need to synchronize on the push top stream, and then we can send our data to our top neighbor. And conversely, we just then need to synchronize on our push bottom stream to send the data to our bottom neighbor. And meanwhile, we hope that the computation is still running on the main compute stream and we can overlap this. And indeed, if we then look at the profile again, you'll see 3 things that have changed. You have these 2 smaller kernels, which are also the Jacobi kernel, but now they're running before the main computation runs. And then we have the MPI operations, MPI send receive in here, that can now take place while the actual main computation is still running. And so in a sense, we now have overlapped this, and hopefully that gave us better efficiency. So when I talk about efficiency, let me just explain what you see on this chart here. So I have the efficiency just from 80% starting, so this is not from 0%. And efficiency means, in a sense, how well can you scale up when you use more resources? So how does the runtime when I when I go from 1 to 2 GPUs, does it halve or does it improve less than that? And that's essentially my parallel efficiency. And you'll also notice this is not at 100% because we compare to the best serial baseline we can do here. But if you now notice that we go from 1 GPU up to 8 GPUs, and we compare on the left side the MPI and on the right the MPI overlap implementation, that the further we go, the bigger the gap in efficiency is, because when we go to more GPUs, the local part we need to compute gets smaller. And so the fraction of time we spend communicating becomes more important. And so if we can hide this while doing the computation, we can gain parallel efficiency and get better, strong scaling in here. So, but we are not done yet, because we still have some synchronizations that we would like to get rid of, but we can't really at this point, because if we were to remove these CUDA stream synchronized calls here, we would jeopardize the correctness of our computation, as MPI send receive does not have a stream argument. So I cannot just enqueue this argument on a stream and have it order automatically in sequence with the computations I need to perform before I can actually send the data out. So I still need to synchronize streams here. And one solution to get around this is to use a library such as Nickel, which we'll look at next now. And Nickel is short for the NVIDIA Collective Communication Library. So the name comes from the fact that when it was first conceived, it was essentially meant to be the fastest way to do collectives such as all reduce on the GPU, because many deep learning codes were needing these. But over the releases and the years, support has been added also and is present now since quite a while for regular point-to-point send receive calls. But the core fact is that Nickel uses GPU kernels for communication. So it tries to aggregate, as we'll see, all the kind of communications you will do into a kernel that is also running on a stream on the GPU. And for us, important here in this example is that we can run on a stream, and so take advantage of just the natural ordering operations on a CUDA stream. Let's look at how we can get started using nickel. There are several ways you can do it, but the simplest, if you already have an MPI application, you just reuse what you already have done with MPI setup. So you have the MPI convert, size, and rank. And nickel requires you to create a unique ID on one of the ranks, here on rank 0. And then it's on you to take this unique ID and distribute it, in this case with a broadcast, across all the ranks in our com world. We make sure every rank has seen this ID, and then we can create, consequently, out of this com world, create a nickel communicator with the same size and rank of the original MPI communicator and taken in this UID. We can then do nickel communication operations and finally destroy the nickel communicator and finalize MPI. And that's all you need to also add nickel, because you can use both nickel and MPI in the same program if you want to. So that is how to get it set up. Then one thing that in nickel you can do is you can group operations together, and that can be used for several things. So one of these is because you launch a kernel to do the communication. If you group the operations together, you need less kernel launches and only need to pay a launch overhead once. And it also allows more optimizations on how to best use the available NVLinks and resources to push the traffic around. So in this case, here's an example of just having a for loop and queuing multiple nickel all reduce calls here on the same nickel stream. But you could also use it for other operations, as we'll see in just the next slide. And once you've done the nickel group end, the operations are posted on the stream, not before. So take care of that if you want to enqueue a kernel that's running on the same stream and relies on the communication being complete. In this case, we just then synchronize to finish communicating, but after the group end, we are now fine to do other operations and enqueue them on the stream. And in our case, we're not doing all reduces, but we are doing point-to-point communication. Yeah, go ahead, Markus.
Sure. Sorry, I just had some questions. So it seems to me like the scope of what nickel does, because like historically I've seen it pitched like, oh, this is like the optimized all reduced library, but what you're suggesting here is it's actually closer to a scheduling library for comms, where you tell that these are the computations I want to run, and then what it takes care of is making sure comms is overlapped and then synchronizing correctly. Would that be correct, or question?
So nickel is at this point just a general communications library optimized for GPU buffers. It still has the goal is to have the fastest all reduce, and I think it's doing fine at that. But you can so overlapping communication and computation, you still need to carry yourself to choose different streams. I have an example on that just in a bit, but generally, what it is very good at is understanding the topology of the system, how your GPUs are connected, and then choosing the best way to kind of move data around your whole system. So inside a node, across multiple nodes, and you can just use things like the group start and group end to kind of give it more information of which operations can be batched together, so that might be able to do something more efficient with this.
So presumably, if within the group start I do an all reduce, then I do like some other, I don't know, scatter operation or something. What happens then? Is it?
Yeah. So it can group those together in one kernel launch for. So for once, what actually happens, I think I would need to refer to the profiler or the nickel devs. I think they will also appear on this in a later talk. But yeah, it will just try to do the most efficient thing, how to move the data that's needed for both operations around.
And since you've mentioned launch overhead a few times, like I'm wondering, should people think about it like a bit differently for a single GPU versus like multi GPU? Like, is there more overhead in multi GPU?
Not necessarily, because we are still just talking here to one GPU. So this is each process is doing this on its own with its own GPU. The thing is just if you looked at the performance comparison between the MPI overlap and non-overlap version. So the further we go out, the less computation we have when we strong scale. So when we reduce our local simulation domain by splitting it over multiple GPUs. And so when latencies were not important, maybe for 2 GPUs, they start becoming more important the shorter your actual computation gets. So the less latencies you need to pay for, the better in this case. And launch latency in this is just here the case when you have some overhead to launch a kernel on the GPU, because you still need to enqueue the operations on the CPU. And so if you only do this once, you only pay the launch overhead once. That's just
So when you say latency, does this also include like startup latency, as in like peers establishing each other, does that count as latency, or is that just like a one-time cost?
So that peer establishing, I think, is more a one-time cost, but I'm just counting general latency. So I tell it to do the operation, and how long do I have to wait before the operation starts? And that can a couple microseconds to launch a GPU kernel. So same for other GPU kernels, basically. And yeah, and there are other ways, of course, to mitigate that. I'm not going into CUDA graphs today, but you can also use Nickel with CUDA graphs, which allows you to kind of pay even less launch overhead if you do have multiple calls and so on, and kernels mixed with computation. But there's examples in the other talks I linked at the beginning.
Sounds good.
Yeah.
Thank you.
Cool. All right. So yeah, that's a very good question, because the overlapping part we will still need to take care of, as we'll see. But for now, I just have the example of what we need to modify in our Jacobi solver to be able to use a Nickel instead of MPI. So we do have our kernel launch here, and this is just the version that launches one kernel for the whole domain. We can get rid of the stream synchronize, because inside this Nickel group start, we do the equivalent of the two MPI send receive calls. Nickel doesn't have a combined send receive call, but instead we just use this group start mechanism to post the receive and the send, and another receive and send for the other part of the domain. And we enqueue all these operations on the compute stream. So essentially, we've just launched one communications kernel here that will take care of pushing the halo rows around across all ranks. Take care that Nickel doesn't have a tag parameter here to match up receives and sends. So I do need to take care that I have them in the right order, because if I just launch it with two GPUs, I don't want to have the data from one send landing at the wrong receive. So this is just why they should match up in the order here. But this is essentially the conversion of the MPI send receive to Nickel. And going back again to our parallel efficiency chart, so still the same axis, efficiency and number of GPUs, MPI overlap, and now the new Nickel version. You can see that Nickel already does quite well. But as we go out further and further to multiple GPUs, the MPI overlap version still remains the most efficient. And so that shows that we still need to take care that we understand kind of what is the critical path, what is exposed, which kind of communication can still be overlapped with computation. And so the next step here is that we will actually look at the profile again. And we see that we have the Jacobi kernel. We have the Nickel kernel now, so that is new. We don't have any MPI operations in here. And we want to try to have this Nickel kernel also overlap with the concurrently running computation for the domain. We use the same technique. We want to try to slice off the top and bottom rows. But now we have to take care of one additional fact, and that is that by default, all streams are equal, and there's no kind of preference that we can make sure that the two small kernels that compute the boundaries are done first. So to ensure that they are done first, we need to use another feature called stream priority. We query first what's the least and the greatest priority, and then we have two separate streams, compute stream and push stream, and we give compute stream the least priority, and the push stream that's responsible for the boundary layer and the actual communication the highest priority. And if we now launch our kernels, you'll see that here the highlighted kernel argument is different for the two small kernels that each compute the top and bottom row, and the bulk of the computation is on compute stream still. And then we enqueue the Nickel operations also on the push stream, so thereby ensuring they are ordered and only execute after we have these boundary layers ready. And then if you look at the profiler again, we can see now that we have, again, this overlap. So we have two more kernels. We have the boundary kernels here, the main kernel, and then after a while, we have the Nickel kernel for the send receive. And if we hadn't done the priorities, it could have easily happened that all these kernels just execute at the very end, because this bulk kernel here for the interior computation can just use the whole GPU resources. And so when it runs to completion, that would be too late to overlap this communication kernel here. So having done that, let's go back and check how we are doing in terms of efficiency. And we have now this new bar here for the Nickel overlap version. And as we can see now, we're doing quite well, and we even managed to get a bit of a small advantage, but it's there. And remember, this is still just Jacobi solver as a toy application. But we still managed to get a better parallel efficiency even compared to the overlap MPI version. All right, so as we can see, the technique overlapping is still important. We still need to understand which parts are independent and how we can hide those latencies. But nickel allows us, by using the stream ordered interface here, to just also simplify and get rid of some of the synchronizers we needed before. For an example of how a production application uses nickel, there's a software package called VASP, which is very widely used for electronic structure calculations, think like simulating material properties, predicting them. And VASP has been using CUDA-aware MPI, and using nickel, they saw some of the benefits we looked at here. So you can first do the asynchronous execution, and you don't need to ensure so much synchronization between MPI and nickel because you can just use streams. We didn't use any of the collectives here, but of course you can also use them. And if you need them, already used on the GPU is then much faster if you can use it with nickel. And yeah, the stream-aware interface also generally reduces the need for synchronization. And so if you look at the performance, they managed to get up to 2.6x increase or decrease in time needed on 32 nodes in this case for this particular compound crystal they were simulating. And there's lots more of investigations if you're curious on what kind of metrics you can think about implementing this on this blog post here. But the bottom line is they think they didn't see a downside to using nickel, and for scaling up out of a node, there was a benefit due to all these kinds of things we talked about. So that is what I wanted to talk to you about for nickel. And now we come to the third programming model, which is a bit different from the two we looked at before. It's called NVSHMEM. And NVSHMEM is something we call a partition global address space library, or PGAS for short. So it's an implementation of the OpenSHMEM standard, but PGAS means that your address space kind of pretends that it's one address space, but it's partitioned into multiple parts that make up this symmetric heap, so where dynamically allocated objects are stored across multiple GPUs. The jargon is a bit different. This is not called a rank in SHMEM. It's called a PE, processing element. And as you can see, we have these n GPUs, and we have the symmetric heap that's managed by NVSHMEM. And so if we want to use an object that can be communicated between these different processing elements, GPUs, we call NVSHMEM malloc to get the memory for it. And then one rank can simply access the allocation from, one PE can simply access the allocation from another PE. You can still do CUDA malloc for private memory that's not partaking in communication. But the important part is that you have this kind of special allocator you need to use here. And what this enables is, as NVSHMEM is not two-sided communication, but one-sided communication, so you don't actually need to post a matching receive for your send. You can simply say NVSHMEM put or NVSHMEM get, and then the data will just be marshaled over the network or over whatever interconnect is used in this case, and then will appear in the other PE's memory space and the symmetric heap. You can also use it at the same time with MPI, so you don't need to use it as an either or. And in fact, the most common way to initialize can also use MPI again. Just as an example of what else this can do, because one thing that's new that we haven't had in the other libraries before is CUDA kernel interfaces. So you can actually do communication directly from your CUDA kernel. And so if you look at a timeline from here, from top to bottom of how that could look like, what this enables you is you can launch a CUDA kernel once, pay only the launch latency we talked about just once, and wait for the kernel to complete. And you don't actually need necessarily another kernel or another section to do communication, as you can just have interleaved computation and communication, but on a very finely grained basis within that kernel. So it can simplify implementation of your algorithm, and it can also enable optimizations such as kernel fusion, and that can give you a big speed up, as we'll see with another application example in the end. So let's say,
and presumably, Markus, this is like where the composability angle comes in too, right? Like people should because I think people might think, oh, I should use nickel versus NVSHMEM. You're just saying are you communicating within the kernel or outside of the kernel seems to be the right framing, right?
Yeah, I would say. I mean, NVSHMEM also has a host-side API you can use similarly to nickel. But really the main point is if you want to in-kernel communication, although there's, I will have a bit more on that in the end, but yeah, that's kind of decide what kind of pattern you need and then pick a library, but you can also interoperate between libraries if you need to.
So why do you need a launcher then? Like I thought that was quite strange when you first brought it up. I'm curious.
The NVSHMEM run, you mean?
Yes.
Yeah, so that's just a mechanism to make sure you have all the processes launched that are supposed to communicate with each other. So, I mean, if you just launch your application in a shell on node 1 and on node 0, right? How are they supposed to be known to each other? So somebody needs to tell the process on the first node that there is a process on the second node that it can communicate with. And these launchers do basically this under the covers. So they make sure that the processes know where to reach each other.
Well,
Yeah.
Sorry, maybe I should rephrase my question. It seems like the launchers you mentioned are like they almost seem like aliases of each other to me. Like they're the same launcher under the hood. Is that true or not really?
Can be to a certain extent. I think for MPI and NVSHMEM, they are different programs, different code, but all of these also you can use if you have a cluster that uses cluster scheduling software like Slurm, for example, or let's say Kubernetes. I mean, they all have different jobs, but they need to accomplish one thing also to be able to, the user tells it to launch jobs spread in a certain way over the different nodes of the cluster, right? And then somebody needs to tell these processes how they can reach the other processes. And this is kind of the commonality, I would say, between the different launches. So that you could do it manually. You could open a socket and rely on convention, So this is kind of, but this is hidden. You just call MPI init and you call NVSHMEM run and so on. And then you don't need to take care of this very low level instrumentation. And if you have a lot of processes, you need to launch millions of them, maybe it can also be quite challenging to have them all come up at the same time efficiently and so on. So this is one other thing that these launchers need to do. Yeah. All right. So yeah, but at this point, we are in our application. We can launch a kernel that's not using NVSHMEM. Well, we want to run a kernel that can launch NVSHMEM, but before we can do that, we need to, again, initialize NVSHMEM. And this is also here the skeleton that allows you to either start from an existing MPI, MPI communicator. So you can see we grab a MPI communicator here in a variable, and we have an NVSHMEM specific struct where we attach this as an attribute, and then we can initialize NVSHMEM with that communicator. And in the end, these asserts will be true. So the size and the rank of the MPI communicator will correspond to the returns of how many PEs NVSHMEM thinks there are and what rank my PE is. There's also a way to do it similarly to Nickel, where you can initialize it with a unique ID, but then you also need to do a broadcast again of that unique ID. And so if you have a different way to broadcast, you can use that. You could also use an MPI broadcast, but in this case, it's better to just use the MPI-specific initialization mechanism. And of course, because it is based on OpenSHMEM, you can also use it to interoperate with OpenSHMEM or the SHMEM standard, which is more for CPU-side communication then. And if we now look at an example of how that would look like in such a kernel, so in the Jacobi kernel, this example is a bit condensed. So we just imagine that the compute part here is responsible for the update of the Jacobi stencil. But what we want to focus on here is really the way that the communication is done. So just so we have less lines of code to focus on here. And the interesting part about NVSHMEM is that from within a kernel, you can now do thread level communication. And this NVSHMEM float P operation essentially transfers a single float from the local array U here in this case to the remote array U on another PE, and the same for top PE and bottom PE. And this is done by each of the threads that make up the top and bottom rows. So for NVSHMEM, you can do this now. On NVLink Fabric, on DGX systems, for example, this is an efficient thing because it maps to a load and store operation over NVLink essentially. And all you need to do then is really launch the kernel and have a way to synchronize to make sure afterwards from each iteration that you are done communicating. So that is in that sense, it simplifies your algorithm. So let's look at how this looks like in Jacobi when we implement this single element put on our DGX system. And at a first glance, it looks like this is a bit disappointing because we don't reach a high parallel efficiency here. But there are several reasons why we see that here. So the first one is that in our Jacobi app, we really just have one single kernel, and we can't use one of the major advantages that we could just fuse maybe two separate kernels together because we can do communication interleaved with the computation without relaunching a kernel and paying those overheads. And the second thing that's interesting is the baseline efficiency here is already a bit lower than the others. But if you look at how it looks like when you go up to 8 GPUs, you don't lose a lot of efficiency. And in fact, for 8 GPUs, you are quite close already to the MPI version. So there are ways to make the baseline more efficient. And in one of the talks I linked at the beginning, Jerry did just that and looked at several things you can do to, for example, use link time optimization to make calling these NVSHMEM functions more efficient from your kernel, and which recovers quite a bit of performance and makes even the Jacobi version look a lot better. But I have also a real application example in the end where you will see quite a bit of a performance gain by using NVSHMEM. Before we go to that, though, I want to show two other ways you can communicate from your kernel. So the second one is, and please focus here on these parts. So instead of just having one element sent by each thread, we can also bundle up several of these operations and do communication cooperatively between blocks. So this is why this is now called float put NVI block. And the reason this is this API exists is because interconnects that are not NVLink, so if you go over the fabric, if you go over InfiniBand, these networks are designed more to transfer larger messages, and then this allows them to reach higher efficiency, higher performance. And so this is a way you can still use NVSHMEM and still have a sort of flexibility on how finely grained you communicate if you do it on a block level. And as you can see, this is the parameter for many elements we transfer here. So we transfer one element per thread and still the same kind of boundary exchange, and still after the kernel have the same kind of synchronization call to wait for communication to complete and to go into the next iteration. This is still having us have a host side loop to launch the kernel and synchronize, but we can go even one step further and put everything just into one, basically one giant kernel. And in this case, we have to do the synchronization across different PEs within this kernel. So you can see that the for loop over iterations is now inside our kernel launch. We have the swap, buffers, and compute part, and the communication part is essentially unchanged. But what we have to do now is we have to be clever with synchronizing. So we exchange data, and then we do something where we check if we are the block 0 here in this case. So if we are, if our block is in the actual row here that is exchanging data with the neighbors, so in the first or in the last row, and then we make sure that all threads are here converged and that we have finished the outstanding communication operations. And then we do for one thread in each of these blocks, so index in X and Y direction in that block is 0, we do something with an NVSHMEM atomic increment on a newly introduced sync variable. So the sync variable is really just a new integer pointer we passed into the kernel here at this place. And we increment the sync variable on the remote top PE and on the bottom PE, so on our both neighbors. And we do this because now it enables us to implement synchronizing our nearest neighbors by just waiting until the sync variable has reached a certain value. So this is the sync variable, and we compare until it's greater than this value. And the reason this is the value you need to wait for is because we have two neighbors, so we expect two increments of our sync variables from top and bottom. Then we expect one increment per block, and the number of blocks in the grid is griddim.x. And since we don't reset this variable, we expect it to increase by this amount each iteration. And so this is one way it can be done to implement such an in-kernel synchronization. There are, of course, different strategies you can think of, and what really works well depends on your actual application. But that allows you to really just have one kernel that continues running until the full computation is done and finished. And as an example of an application that has done just that, to fuse kernels and move everything into one kernel, there's CUDA, which is CUDA with a Q, which is lattice quantum chromodynamics code. So they do simulations that have an interesting property that they need to strong scale out very far. And strong scaling is hard in the sense that the further you go, the more GPUs you use, the more important all these communication latencies come. So, and they use the device-initiated communication to try to overcome these latency barriers. And there's a whole GTC talk on how they did that. But if you look at what this results and what the difference is, so here we have just a screenshot from such a profile. You can see we have in blue these kernel calls for packing kernel. Then we have different data copies through CUDA-aware MPI. So this still happens here, overlapped even with another kernel. So they did to great length to optimize that already. Then you have another couple of kernel calls for the exterior and some other MPI calls, and then you go into the next part. But if you now look at the difference of how they implemented this with NVSHMEM, you have a fully fused kernel, and that kernel does all of that from before and uses in-kernel communication, so you don't see MPI activity here in this row. And in the case of CUDA, which also uses lower precision floating point values, so in this case, especially, you have less and less data to work on, and it gives a big speed up the further you scale out, because what this plot here shows is essentially the performance, gigaflops per second, across the number of GPUs that the code runs on the x-axis. And because this is strong scaling, we start out with a same fixed global problem size and divide this by the number of GPUs. And at 512 GPUs, you see over the MPI implementation, there's up to 1.6, 1.7x speed up just by using NVSHMEM and fusing those kernels, introducing other overheads. So this is really where in-kernel communication can help you make your kernels faster. I want to, now that we have looked at all these three programming models, still give a bit of a comparison between them, how they look like, or how they look quite similar before I wrap up. So first we looked at MPI, and MPI has different APIs. We looked at send receive. In this case, we have it separate in the send receive call. You can use host and device buffers, so you can use it for CPU and GPU buffers. And it has this concept of communicators to identify ranks that talk to each other. This is very similar to how Nickel looks like, although Nickel operates just only on device buffers. You have a similar concept to the communicator in Nickel. But in addition, and this is very important, we have the stream parameter. So you can now have your communication be stream aware and have it automatically scheduled according to how you enqueue kernels and communication into the same stream. Lastly, NVSHMEM is a bit different in that it also has a sort of like what you could see as a send call, but in reality, this is called one-sided communication, as the receiver doesn't need to do anything. The receiving PE is completely passive, and it will just receive this message when it basically has arrived. You can, of course, synchronize to wait until it has arrived, but you don't need to do anything special like post or receive. And NVSHMEM also allows you to do in-kernel communication. So to summarize and maybe give you a bit of a head start on which library to use. So all of these are good choices, are supported, and can give you very high performance. It depends a bit on if you have any extra requirements, if you should start with one over the other, I would say. So if you're writing a new code, if you have an existing code that maybe already uses MPI on the CPU side, then it's a very easy transition to just introduce CUDA-aware MPI, use it on GPU buffers, and just get your code running more efficiently. But then if you need stream awareness, you should look at Nickel, which you can also interoperate with MPI. Nickel has highly performed collectives. It works on GPU buffers, and due to the streams, you might be able to shave off some more synchronizations you don't need anymore. And for NVSHMEM, there's firstly the one-sided communication model, which might be simpler to use to just implement your algorithm, and it also has the advantage you can do in-kernel communication. So I just want to make sure that you get that this is not an either-or, so you can interoperate between these different libraries how you need them. And it's also not fully as clear-cut, which I omitted in the previous slides just to make it a bit simpler to understand initially, because there are also plans to add one-sided communications in Nickel and discussions how streams could fit into the MPI model, such as discussed by the MPI Forum Hybrid Working Group, or in some GTC talks. You can also look at what the plans look like for Nickel. And there are, of course, many, many more resources on any of these topics here on the websites and the other GTC talks. And if you want to try out these programming models yourself, I would encourage you to check out our GitHub repository of the multi-GPU programming models, where you can find all of the variants of the Jacobi solver fully implemented. So for MPI, for Nickel, for NVSHMEM, and also for some other. And you can play around with those, learn how they work, and try to understand their performance behavior. Yeah, there's also another tutorial based on this that we've been doing for quite a while at conferences. So this is supposed to be a full day tutorial, but it also has some examples with blank spots where you kind of have a to-do and need to figure out how to solve it. and the solutions to these exercises. So if you want to do this on your own pace, you are welcome to check this out and let me know if you have any questions. So yeah, I think we're at the end of the material I had prepared. I'm happy to take any other questions, and thank you for your attention.
Sweet. Thank you so much, Markus.
Sure.
Folks, I do have to apologize. Like the reason why the talk was shorter than expected was like just because I have to run to a workshop. But thank you, Markus, for putting all the contents like so neatly. And I guess we'll get slides and we'll post them in the group as well,
Sure.
so people can go take a look.
I'll let you get I'll get you the PDF and.
Yeah, I guess like Vikram. Well, I guess like a question I have on my end is kind of like, what do we expect? Like the way a lot of people seem to interact with like distributed like libraries like Nickel, for instance, is historically via higher level libraries such as like JAX or PyTorch.
Right. Yeah.
And basically there's sort of like a few good kernels that need to be written effectively, like things like all reduce.
Yeah.
And so like I'm sort of wondering here, like with sort of evolutions like NVSHMEM, do you sort of expect a lot more lower level code needs to be written by people, or is it basically, again, there's going to be like a few good lower level APIs that higher level libraries will adopt, and that's pretty much it?
Yeah. I think ideally, and I didn't explicitly point this out, though, thanks for mentioning it. Yeah, if you can, of course, stay with the higher level library. I mean, they have been battle tested and implemented to be as efficient as possible. But I would say at some point, maybe if you want to extend something, you work on these libraries yourself, you want to work on these libraries yourself, or you want to just do a project on your own that just doesn't have a library dependency, or even just to build your mental model of how these kind of higher level frameworks do the magic under the hood, then I think this is why I think it's useful to have an overview of these models. But if what you need to do is already implemented in any of the high level frameworks, then by all means, I would say use that and don't reinvent the wheel, except if you're curious, then of course, just go ahead. Yeah.
But then there are few people who go a bit more ninja to get that last 2% to 5% benefit.
Yeah.
So if you're in that category, then going to the lower level gives you that benefit that you're seeking. Because there are certain overheads that comes from the higher level libraries that do not get exposed. Usually this happens when you have a large cluster and a tons of GPUs that you want to maximize for your cost over there. Saving 1% or 2% is actually a huge revenue number. So those are the people who spend significant effort to make that happen.
Yeah. But in my experience, those are also the people you don't need to explicitly tell. You rather need to stop them from doing that stuff because they will just go off on their own and tag around, right?
Yep.
Yeah, for what it's worth, I'm just Googling now. I did notice that y'all shipped a library called NVSHMEM for Pi, which just sort of makes it like, doesn't look too crazy.
It's basically a Python front end for NVSHMEM. So you have APIs in the C++. Now we have APIs from the Python so that Coda Python and other people in that space can actually leverage and use just at the higher level itself. But it still is a much more lower level. But there are many people who are non-PyTorch in the Python world who wants to use device-initiated communication. So.
All right. I don't see any more questions.
Mark, there are a couple of questions in the chat if you want to pick up.
Maybe do you want to go ahead and read them? I'm not.
So there is one question, Markus. I think this is for you most likely. I'm curious on how NVIDIA views future of interplay between PyTorch, symmetric memory, NVSHMEM, Nickel, symmetric memory with window API. Is it a matter of what user wants, or would you choose one over the other? What are the trade-offs fundamentally?
I don't really know the answer to that because I'm not so close to these teams, so I would just need to ask them myself. Just from performance perspective, I think the teams do what makes sense, right? If you need to reduce latencies from the critical path, you investigate how you can get rid of those. And this is kind of also how these libraries are born in the first place. So you want a high performing all reduce, Nickel was born that way. You want to reduce more synchronization, put better overlap, get less latencies, you have NVSHMEM to do in-kernel communication. And I think just from these first principles is how usually libraries evolve. But for the concrete plans, I unfortunately don't know them for the teams.
I think there is a clarification question. Do we need for any NVSHMEM collective launch the cooperative group to be made available, and then you should be launching? So should we use cooperative groups or not?
You can use them. What I didn't show is the launch for the actual kernel. So because if you want to do in-kernel synchronization, you need to make sure that all the threads that need to be synchronized are also scheduled right now on the GPU. So there's some more details in the NVSHMEM documentation, which I would say is if you want to use it, you will figure it out. But just important to point out also that this is another kind of cooperation before you actually get to the thread groups. Yeah.
All right. Thank you, everyone, for nice questions.
Thanks very much.
Yeah, if you have any more questions, please let us know.
Good, sweet. Thank you for coming in, Markus.
Yeah,
so
sure.
If
Thanks for having me.
If any question, please, please feel free to message him. And if you'd like more sort of distributed talks, like feel free to ping Vikram as well. Otherwise, yeah, we'll see everyone next week. And thanks, folks. Thank you again, Markus.
Thanks, everyone.
Thank you.
Bye-bye.